So welcome everybody to the final day of this workshop. So essentially, up to now, we have been dealing with what's known as the forward problem, right? We have been building models and then simulating them forward in time, and just plotting simulation results. But for this last session, we will work on the inverse problem, and that's it. Given a model and given some data, what is the how can we retrieve or fit the model to the data so we can retrieve model parameters that actually when the model simulates, then the result of the simulation matches that data, right? And dynamic causal modeling is a way of doing this, and it can essentially accommodate any type of time series that we typically use in neuroscience. So most common cases will be electrophysiological data or imaging data. So fMRI and EEG experiments heavily make use of DCM. And as I said, the challenge is to find the best model parameters for your model, to make your model look like the data. And DCM does that in a Bayesian manner. It follows at least this Bayesian formalism, and I'll talk more about this in a second. And it's using state space models. I'll show you an example of state space model, but you can think of them as a discretized version of the differential equations, right? In state space models, we have the state at one time point and how that depends on states at the previous time points. So we have this almost discrete evolution in steps. And it's also a method that gives us back effective connectivity. And especially if you're coming from the neuroimaging field, you will probably be more familiar with this. But what we mean by effective connectivity is essentially a metric of connectivity between regions in the brain that is driven by a model, right? So it is more than just correlations between those regions. So for instance, here on the right we see some voxel-based activity out of 3 regions in the brain, right? And typically, an easy thing to do is to calculate the functional connectivity between them, which is just taking correlations between pairs of these, and then seeing how well correlated or anti-correlated these regions are. But that's a purely statistical measure. With DCM, we add a model into the mix, right? And this model comes from our hypothesis about the dynamics of each one of these regions. So when we actually build the final graph of the model, as you can see here, with these 4 regions, and we add any input, like the U1s and the U2s here. Inputs can be either external inputs, completely external to the brain, or they just can be inputs from inside the brain that we're not modeling, like we did yesterday with the Poisson spike trains, right? Those spike trains are coming from inside the brain. It's just they're coming from populations that we don't model explicitly. So when you build a model like this, like a more biophysical model, and you feed this model to data, what you get back is the effective connectivity, because and that's a more reliable measure, I would say, of the actual connectivity between these regions, because it doesn't just rely on summary statistics. It looks into the dynamics of the neuron over time and figures out how they are connected. So as I was saying, DCM, and particularly the spectral DCM that we will look into now, is built of state space models. And here you can see an example of a state space model expressed as a differential equation this time. This is a bilinear model, right? Because it has the linear term, which is the A times X, but it also has this bilinear term of the U times B times X, right? So as I said, U's are external inputs or inputs from populations that we don't explicitly model. C is the input weights. B, this bilinear term, is essentially the effective connectivity as it is modulated by the inputs. That's why we have the input multiplier. And A is the effective connectivity between regions, like given no input, right? This is independent of inputs. And the main goal of DCM is to give you back these A and B matrices. So this is how you can tell how your network is actually structured, by looking into the A, if you care about the the case of connectivity without any inputs, or looking into the combination of A and B if you also care about some specific inputs. Now, the assumption that it makes is that it assumes that there is a weak stationarity in your signal, and that means that the cross-spectral density essentially for any finite amount of measured time that you have, say in a bold experiment, that remains constant. It assumes bilinearity, and this is essentially the introduction of this B matrix here, where it allows for this input modulated connectivity. And it also it assumes Gaussianity, and that basically means that all of the parameters that we're fitting, right, during the DCM process, we assume that they come from a normal distribution, and that's, in other words, the Laplace approximation. Now here I'd like to show you essentially on the left how a typical pipeline of DCM works on bold data, and on the right we have the equivalent snippets of code from NeuroBlox itself. So we start from the actual neural dynamics, right? And our default is to use this neural mass model, which is exactly this equation here, or written in NeuroBlox here. You see this dx equals to JCN, because as you've seen in previous days, JCN can be any input. So as we build the circuit, stitch together multiple of these linear mass models, we will build the A matrix and the B matrix, and any C matrix if that's also included. And now below that, right? So the result of this is some population average neural activity, right? This is just a neural mass model. But then we move into the hemodynamic state equations. So this is what is called the balloon model. So this model will essentially model the dilation of blood vessels, and will model blood flow in the brain, given parameters of the neural mass, right? Specifically for this region that we're modeling with the neural mass. And on top of the balloon model, we have the bold signal, right? So essentially, we take the results of the balloon model and we transform them to bold, which is actually a quantity measured in fMRI, right? So this is essentially the pipeline that helps us move from a neural mass scale all the way, well, up essentially the hierarchy to bold, right? And we can relate our model, our biophysical model, it can be any blocks here, to actual imaging data. And here I'm also showing you the symbolic way that we write the balloon equations to see that it actually matches the math quite easily. So of course the balloon model is not the only model that can actually transform neural activity to bold eventually. You can replace this with other models. So this is what we call an observer model, observer blocks. Sorry. Now, in order to solve the inverse problem and get back, the true parameters for your network, in DCM we perform variational Bayesian approach. So in other words, that means that we assume a specific specific shape of the distribution for the posterior, right? And the posterior distribution in Bayesian terms is always the distribution of the parameters given the data. And this is Bayes' rule. That's equal to a likelihood function, that is the probability of the data given parameters, and any prior that we have over the parameters. So that's the P of probability. And yeah, this product is the important thing. And this product is divided by this normalizing factor, which is the probability of data, right? But in practical applications, because the probability of data is something very hard to calculate, because that assumes no specific parameters, that's the probability of all data in your experiment, we apply this variational Bayes trick, which helps us circumvent essentially the computation of this, because we assume a specific shape of the posterior. Now, after making this assumption, we will perform essentially an optimization. And this optimization is to maximize the negative free energy, which, in other words, in machine learning literature, you can also find this as the evidence lower bound. It's this quantity right here, which, if you expand on the log a bit, you can see that it's the same as the Kullback-Leibler divergence, which is a function that measures the distance between two distributions, right? And in this case, it's the distance between Q, which is our assumption of what the posterior looks like, and essentially the marginal. Sorry, this is not the marginal. This is the combination essentially of the likelihood and the priors together, right? So essentially, we're trying to make this what we have assumed for this quantity as close to possible as the product of these two here. And in order to do this, we apply this Levenberg-Marquardt optimization. So this is what was recommended by the original DCM work, and it does perform better than other approaches like a Gauss-Newton method, which is very common optimization method. But as you can see, for instance, in the case of this posterior distribution, if you apply Gauss-Newton and you start from a point of no high probability density, then this method can drift away and it can lead you astray, basically. But if you follow the Levenberg-Marquardt, even from the same initial point, it actually manages to find the place of the highest probability mass, which is what you want ideally from this method. Now, there are different types of the DCM analysis. The earliest one we had the deterministic DCM, which included simple state space models like the one that I showed you. Then stochastic DCM, which can include nonlinearities and also include stochastic terms in it. But that became, exactly because of the introduction of the stochasticity, that became computationally much heavier. So in other words, it's impossible to run a model with many different regions in this model in any reasonable amount of time. A regression DCM, on the other hand, is very fast, because in regression DCM, we replace the state space model with some simple GLM. That's a generalized linear model. So we do away with a lot of the differential equations, so that's much faster to compute. And the spectral DCM is somewhere in between the others. It allows for stochasticity. It is, in terms of the speed of running, it's in between the deterministic and the regression, but it also maintains biophysical relevance, right? Because we still keep the state space models. And as I was saying, you can add any blocks that you want for any one of your region in your model. Now, in NeuroBlox, we have our own implementation of DCM, right? DCM, it's also originally comes from SPM, which is a statistical package. I believe originally in MATLAB, but there's also a Julia implementation. And here I'm just showing you some performance graph where you can see that our implementation in Julia, we're using modeling toolkit, that's in green, or using not modeling toolkit, but the non-symbolic way of writing differential equations, but still using automatic differentiation, which is actually the novelty here. The original the original implementation of DCM in SPM does not have any automatic differentiation. So both of these implementations, that ours, the orange and green, are much faster than the original one in MATLAB, but they're also faster than the original algorithm implemented in Julia, right? And the importance is that the orange and green overlap. So that tells us that even though we use modeling toolkit, which is the symbolic way, we don't lose performance over the non-symbolic way of writing differential equations. And essentially, this is in spirit with modeling toolkit and in spirit with everything else that we've seen in NeuroBlox. We wrote SP DCM to be very modular. So you can essentially follow this entire pipeline, which you will in the exercises as well. And you can replace parts of it with different parts. For instance, when you define your neuron mass block, you can just replace, say, this set of two equations with your own block. When you build the circuit, of course, you have the freedom to build any circuit that you want. That comes from your hypothesis about which regions of the brain you think are implicated in your experiment. You can provide any measurements that you like, be it electrophysiological ones or imaging ones. And then we give you the option of doing variational inference with automatic differentiation and with the Laplace approximation, and also give you out some metrics so you can tell whether the optimization worked or how much you should trust your results, essentially. And this is also published from our group, so you can check this preprint as well. So finally, I would like to talk about model selection, because say that we make an assumption about the network that our experiments should stimulate, or so the network that should be involved, but we don't know exactly the connectivity within that network, so we can try different configurations. So here you can see the results of trying 3 different configurations and comparing them. And to do the comparison, we essentially print out the free energy functional, right? So smaller values, larger values for the negative free energy are better. So the blue line is the ground truth here, the ground truth model, because this comes from simulated data, right? So we used the blue one to generate some data and then fit all 3. And then the orange is a version of the ground truth model with just 1 connection removed. This was a model with 3 regions, but the orange one has the connection from region 2 to region 1 removed. And model 3 has this connection and also another connection from 2 to 3 removed. So as you can see, the comparison works because as you move further and further away from the ground truth model, the free energy functional becomes worse and worse. And this is the metric that we apply to do model selection at the end of the DCM process. So this was my final slide. So you can navigate to the final session, spectral dynamic causal modeling, and open the relevant notebook, DCM. And yeah, feel free to ask any questions. Thanks.